So hi everyone. I'm very happy to introduce Professor Matt Kusner from the University College London. I just want to introduce him briefly. So Matt Kusner is currently an associate professor in machine learning at the University College London, and his work aims to design simple machine learning models tailored to the constraints of the problem at hand, particularly in causal inference, algorithmic fairness, private learning, and molecular material designs. I think many of you might know his some seminal work, including world movers distance and some fairness thing. I really love those works. But this time, it's not related to that, but I believe this is also very, very cool work. So I'm very excited to Matt to present today's topic. So could you please start, Matt?
Yeah, happy to. Yeah, thank you for the lovely introduction. I'm very excited to be presenting at Riken at this lovely seminar. You all have had such lovely speakers, so thank you for the lovely invitation. This talk is, not about molecules or fairness, but is kind of more aimed at more classical machine learning, at learning binary decision trees. So a problem that's been, addressed since the early days. One of the earlier works, by Bryman in the 60s. So this is work with Valentina Zantadeschi, who's also at University College London and jointly at INRIA in Lille, and with Vlad Nicolay, who is at the University of Amsterdam. Please ask any questions in the chat. Feel free to ask them out loud as well. I can't see your hands or faces, so however you wish to ask, please do. Good, let's start. Okay, let's start by imagining you get a call from mission control. This is, this is a space station, and they really trust you. They call you, presumably in the middle of a mission, and they say, hey, we're going to make another rover. And you say, you're going to make another rover? How many rovers do we need in space at the moment? Are we covering Mars and rovers? And they say, it's not for Mars, it's for Europa. And you respond by saying, interesting, nice work on choosing one of the creepiest of Jupiter's 79 moons. And they say, we need you to make a machine learning algorithm that's going to go on board this rover. And you point to yourself and you say, whoa, okay. Do you want it to be on that computer that you're showing? And they respond by saying, we need a supervised learning model, and it needs to have the following properties for large N, the number of data points, and large D, the dimensionality of your data. One, it needs to be computationally efficient to train and test because Europa is extremely far from the Earth, and we need to minimize communication. So we might need to retrain on the rover. And also we need to make a lot of predictions. So this should be fast. Two, it needs to be low memory because we're sending the rover 500 million miles away. We're not going to send a hard disk with it. Three, it should be easy to visualize and to interpret the model because if the algorithm learns something scientific about Europa, we want to be able to learn it too. And four, it should be near state-of-the-art in generalization. So you start to rack your brain thinking of different models, and maybe the first thing that comes to mind is k-nearest neighbors. It's easy to interpret. It can learn complex nonlinear decision boundaries. It seems perfect. The issue actually is that it actually only satisfies this visualization and interpretability. It's extremely expensive during test time. You have to store your entire training set, and you have to compute distances between every point in your training set. There are, of course, ways to speed this up, but it also doesn't necessarily achieve state-of-the-art accuracy. So you think of another model and the next thing that pops in your head is a linear SVM. This is actually quite good because it satisfies these three boxes. It's efficient, low memory. It's relatively, easy to visualize because it's a linear model, but again, we don't achieve state-of-the-art generalization. So then maybe you think maybe a Gaussian process would be nice. And the only thing we really get back is state-of-the-art generalization. I should add that there's been a lot of nice work on making Gaussian processes faster and faster, but they're still prohibitively expensive for large N and D. And the same goes for neural networks. Now, what about decision trees? Well, with one decision tree, I would argue that it ticks these first three boxes. It is computationally efficient to train and test. They're usually low memory. They're easy to visualize and interpret, but single tree methods, especially for classification, are usually not near state-of-the-art in generalization. The way you usually get something that's close to state-of-the-art is by ensembling, by boosting or bagging these trees. But this comes at a very big cost. In order to tick off that fourth box, you have to sacrifice the second and the third box. You now have many trees to store, and it's very hard to kind of interpret these models. So I just want to take a second and say how much I love decision trees. They've been around since the 70s, like I was saying earlier, and they're still being researched and used. They're being used in places like web search ranking, where I met Makoto, to give results in milliseconds. They're being used in healthcare to estimate causal effects. And of course, our favorite application in machine learning, autonomous driving, because why the heck not? Okay, let's not talk about autonomous driving too much. So the question this talk aims to answer is, can we make a single decision tree better at generalization while not sacrificing these other qualities we want? And to answer this, what we propose is to look at how decision trees are optimized. The real tricky part about decision trees, I argue, is their optimization. Finding an optimal decision tree is known to be NP hard. Today, I see three classes of optimization strategies for decision trees. The first is, maybe the most classic, is greedy optimization. These include methods like CART, classification and regression trees, ID3, C4.5, and they work by looking at the data and picking a split in that data that optimizes some measure, such as if I were to split the first into two groups, could I do it in such a way that I minimize my squared loss, like classification and regression trees? But it's greedy because it does this for every node individually. The second class of optimization methods are probabilistic methods. Methods that relax hard splits, like actually sending half of the data one way and the other half the other, into probabilistic splits. So now the way this works is, each data point has some probability of going to every point in the tree. The way to think about this is, instead of greater than, less than, like in greedy, that to send points left or right, you use a sigmoid function to assign something like a probability. And the third type of method, which are also sort of old, are mixed integer programming methods. And these methods were in response to this issue of decision trees being NP hard. Well, how do I say this? So original decision trees, NP hard to find the optimal tree. So one approach was to approximate everything using greedy methods. Another approach was to sort of simplify the decision tree enough so that you could actually find an optimal decision tree. And this is what mixed integer programming did. So you are you are solving an NP hard problem, but if the problem is small enough, you can actually solve it in some time, in a reasonable amount of time. So we know that what I was saying earlier, greedy methods don't have good generalization because they're splitting without sort of thinking of the entire tree. So what about these other optimization methods? So the way I was saying probabilistic relaxation works, they have this certain probability. So for instance, what I'm showing you right now is a point could, with certain probability, go to each of these nodes, and I'm sort of coloring them darker if they're higher probability and less dark if they're lower probability. So let's imagine this is point 1 in your data set, but in point 2 for your data set, the probabilities of going down the tree could look like this. They could look completely different. So the first input was more likely sent left. This input is more likely sent right. The nice thing is you can train these methods using gradient-based methods because you don't have these non-differentiable points of the greedy trees. It's all smooth with sigmoids. The downside is that it really hurts computational efficiency during training and testing because now every point's going through every part of the tree. These methods, mixed integer programming methods, MIPs, everything's in one big optimization problem. They will find the globally optimal tree, but the cost is either, I should have phrased this as a trade-off, either you don't get state-of-the-art generalization if you simplify your tree enough, or if you don't simplify your tree, you can only train this on, thousands of inputs and tens of features due to computation time or memory. So why do none of these methods tick? Well, first I should ask, does anyone have any questions about optimization for decision trees or anything else I've talked about? If you do, feel free to ask now or in the chat. Okay, so why do none of these methods tick these boxes? What's the fundamental issue? So I think the fundamental problem is that decision trees fundamentally have two different types of parameters. The first type of parameters they have are discrete parameters. And I'm going to start naming these, labeling these now. So let's call the first type of the first set of discrete parameters AT, which indicates whether each tree node T is active or not. So in this tree I'm showing you, A1 is active, but the nodes that are lighter, like A6, they're actually not in the tree, so I'm turning them off using these parameters. So A6 is 0. The other discrete parameters are the paths through the tree. Let's call these ZIT, indicating whether point I reaches node T. 1 if yes, 0 if no. So for instance, this is the path of one point, and the nodes along it, their ZITs equal 1. So they have these discrete parameters, but they also have continuous parameters, specifically the tree splits. Let's call these theta T. So in the non-leaf nodes, they help us decide whether to send points left or right. They also have, finally at the end, a continuous prediction function. Once you get to a leaf node, you make a prediction based on the leaf node. Classically, in like greedy trees, each of these leaf nodes have a predictor. Or you can think of, there being one big predictor for everything. Depending on where you go, you sort of get a different one. So let's call this phi. Now, I argue that the reason prior approaches had issues is because each of them mistreats some of these parameters in an unprincipled way. Specifically, greedy methods, I would argue, mistreat both of these parameters. They have heuristics for learning the tree structure and heuristics for choosing the tree splits. Essentially, they say, you know what, learning discrete structure and continuous splits are hard. here's a bunch of options, and let's just do a lot of hyperparameter tuning to get something that's good enough. And this made a lot of sense classically, right? Because compute power in past history was really different, 70s, 80s, not even 90s, and maybe early 2000s was really different. We didn't have GPUs, and they knew learning an optimal tree was NP hard, so they made approximations that worked. And they worked really well. So I think this was a very smart thing to do. But it had these side effects. So, now it doesn't have state-of-the-art generalization. I would argue probabilistic approaches mistreat discrete parameters. Inputs now are probabilistically routed through the entire tree, which makes growing and structuring the tree a bit hard. What these methods do usually is either grow the tree sort of like in a greedy way, and they alternate between learning the structure and the parameters kind of greedily, and then globally learning those parameters, or they kind of fix the tree structure and then just optimize these parameters. So that's why that makes this a bit more expensive to train. Again, I think this makes a lot of sense because gradient-based methods have shown, gradient-based optimization has been super powerful for deep learning. We want to use that for trees, but it just gets a bit awkward when you have to consider the structure as well. And mixed integer programming methods, I think, mistreat the continuous parameters. When you just have the discrete parameters, you actually get an integer linear program in some cases, which can be solved very efficiently. But as you add the continuous parameters in, you get a mixed integer program. And this gets expensive because you have to do something like recursive branch and bound, and you have to solve linear programming problems for every partition in the bound, which makes it much slower and more memory intensive. So this gave us an idea. Is it possible to use principal optimization techniques for both sets of parameters? Specifically, can we take inspiration from MIP literature to learn the discrete parameters, and take inspiration from the probabilistic literature and do SGD on the continuous parameters? So let's start by looking at the discrete parameters, see if this is possible. Remember, we have two parameters to learn the structure and the paths. So let's look at Z. Actually, Z is a bit easier to look at first. And now let's assume we have a tree with fixed continuous parameters. So we have these fixed theta functions. Now I'm technically overloading. Theta is a function here, but I'm also using theta to represent the parameters of this function. But it's just to simplify this notation. Let me know if that's unclear. Now, when we send a point xi down the tree, we start at the root, we evaluate the split function, theta1, and then we make a decision to send xi to the left or to the right by checking the sign of theta1. So it's negative here. So what we're going to do is we're going to send the point left. Then we evaluate the split function at this. It's positive, so we're going to send the point right. So this is the path of xi, given these fixed split functions. So if we call zi the vector of its for all nodes in the tree, so I'm just taking zit and vectorizing it for all t, it would look like this for this particular input, right? I'm going through the first node, the second node, and then if I kind of count top to bottom, left to right, also then the fifth node. The question is, can we learn this using integer programming methods? And we can actually use an integer linear program. So my claim is that it's possible to learn this vector, zi, by maximizing its inner product with some other vector, q, which I haven't told you about yet, but I will introduce. Here's how we define this q. First, for any node t, define rt as the split values of all ancestors to t that split right. So I'll give you a very specific example. So R5, this is the fifth node. the value of all ancestors that split right, its only ancestor that splits right is the second node, and the value of the split function is 1.2. So R5 is just going to be 1.2. And similarly, we're going to define LT, but instead of the value of the splits of the nodes that split left, it's going to be the negative split value. So LT will be 0.5 instead of negative 0.5 because only the first node split left. Now QT is just the minimum of all of the values in LT and RT. So Q5 is just 0.5. Now, if you compute QT like this for every node, and always define Q1 to be 1, because we have to go through the first node, then what happens is something quite nice. You find that only the Qs along the correct path are positive, and all the other Qs are negative. So I'm showing you all of the Qs now for and only the ones along that correct path are positive. And that means that when you solve the integer linear program at the top right, only the z's corresponding to the correct path will be 1 to maximize the inner product, and the rest will be 0 to turn off all of the negative q's. We prove this formally in the paper, but the main idea is that these q's negate negative split values getting to the leaf node, and they keep the positive split values along the nodes splitting right, but along different paths, they create negative split values somewhere along the way. So this is how we learn the z's. How do we learn a's? This is actually super easy. We just have to add 2 constraints to that integer linear program I showed you. Apart from being binary, A has to also respect the tree structure. So specifically, if I make A3 0, then we must have that A6 and A7 are 0 as well. I turn off a node, all of its children have to turn off. We can add this as a constraint between parent and child values. Specifically, all we have to do is take any AT and upper bound it by its parent's AT. So if its parent AT is 0, then the children, which have to be less than their parent according to this first constraint, also have to be 0 because the A's are either 0 or 1. And the second constraint, so that's the first constraint, apart from AT being binary as well. And the second constraint is that we also need the Z's to respect this tree structure. So if A3 is 0, then of course ZI3 for any I has to be 0. Nothing can reach that node. So like before, we can upper bound the Z's by the A's. So the Z's are never 1 when the A's are 0. They have to be 0 as well. So now we actually need to encourage nodes to be turned off, right? So we can solve this optimization problem, but A never appears in the objective. And what we can think of pruning as is as regularization. So we can add a regularizer to this objective. And what happens now is that as lambda is made larger, the optimization will turn off more and more A as the norm dominates the objective. For lambda 0, no nodes are going to be removed. So I think this is pretty nice because this describes how to learn all the discrete parameters in your tree, given fixed continuous split parameters, right? Q is a function of these split parameters. So here's what the full optimization problem for discrete parameters looks like when I sum over my data set. Or in practice, I won't sum over my entire data set, I will sum over a batch of points. So otherwise this might get quite expensive. So you can think of n as the size of the batch. And all we have to do now is figure out how to optimize the continuous parameters, these split parameters, which remember come in through the Qs right there. Now, mixed integer programming methods would optimize theta using branch and bound. We know this is slow, so we're not going to do that. Instead, a principled way to optimize theta is SGD, but we can't do SGD in an integer linear program. This is a combinatorial optimization problem. We can't take gradients because our variables a and z are only defined at individual points, these vectors of 0 and 1, and nowhere in between. To fix this, we've first proposed to do the obvious thing, which is called interval relaxation. And here the idea is just to relax the binary constraints on z and a to interval constraints. So z, instead of being only 0 and 1, it could be anything between 0 and 1 now. And here's a really cool observation. This actually has no impact on the optimization problem. And this is because how we constructed queues. We made all the queues negative except for those on the correct path, which are positive, the correct path of xi. This means that to maximize the objective, z is still going to place as much value as possible onto the positive queues, a value of 1, and it's going to zero out the negative queues. So we haven't actually changed the optimum of this problem. Now, the next thing we need to do is relax a's to the interval, and this does change the optimal solution. This is because the norm on a will continue to penalize a as a is reduced from 1 to 0. And this will interact through z through the constraints, the first constraint. So now this is an upper bound on the original problem because of this relaxation. But this is a pretty, I would argue, standard relaxation for integer programs. Now both a and z are continuous. So the question now is, can we take gradients to learn our continuous parameters theta? So the tricky part is no, because the gradients are actually undefined or 0 for theta. So why is that? So remember, q is a function of theta, and what theta looks like for is this. So for some z, you have a right child and a left child. And when theta goes from negative to positive, these z values flip, right? We said that z is going to try to be 0 or 1, but in order to maximize this inner product. And so the best thing z wants to do is, as soon as theta becomes positive, q becomes positive, it goes from 0 to 1. And so that's what I'm showing you with the right child, and then the opposite will be true of the left child z. So this function is extremely nasty. It has a gradient of 0 everywhere except at 0 where it doesn't have a gradient. And so to fix this, we need to make a second change, which is called, I'm going to call quadratic relaxation. And what this means is we're going to add this following regularizer to the objective. Oh, first of all, before I get into this, is it unclear why we can't solve for, why we can't compute these gradients? If it's not, please ask on the chat or out loud. Please feel free to interrupt me. So we're going to add this regularizer to the objective. And this looks quite odd. So let me give you a few reasons why this is a good regularizer. So this is the sum of the norm of z plus the norm of 1 minus z. When we add this to the objective, z as a function of theta changes from this function to the function on the right. This has a number of nice properties. This makes z symmetric. As theta and q go to 0, this regularizer causes z to go to 1/2, indicating that the point could go down either path. However, this is different from probabilistic trees, which use a sigmoid splitting function, because this relaxation is sparse. In most cases, if theta is large enough, z is either going to be 0 or 1 exactly, not something approaching 0 or 1 like the sigmoid function, except for when theta is uncertain, close to 0. Then we allow it to symmetrically and smoothly change. The second nice thing is this makes the objective strongly convex, so it has a unique maximizer. And from convex duality and Rademacher's theorem, this optimization problem is differentiable almost everywhere. So now we can take meaningful gradients. And at this point, we could be done. We could, there are a number of ways we could solve this. We could use gradient, we could take subgradients, we could do alternating optimization by solving this outer problem for A and Z and solving theta. We could use some generic Argmin differentiation library like OptiNet or CVXPy layers. And we could actually take gradients through this optimization problem and do learning. But we thought we could do a bit better because these methods, they allow you to take any, this is a quadratic program, you can take any quadratic convex program and you can plug in, it'll treat it as a black box and you can take gradients through that program. But we thought we could do a bit better. Specifically, we noticed that this maximization problem can be rewritten as an equivalent minimization problem. This is just algebra, so I won't show you everything, but yeah, just trust me, you can rewrite it this way. So even better, this optimization further reduces to a simpler optimization problem. First, let me rewrite the norms in the second half of the objective by, instead of having the norm, just having the explicit sum over the t that the norm is going to do. So this is the exact same optimization problem. I just wrote out the norm as a sum. And now here's a very interesting observation. Note that the objective and the constraints are separable in Z. Well, what do I mean by separable? What this means is that each of the individual parameters of Z, each ZIT, can be optimized independently of all of the other ZITs. Let me explain. If we fix all of the A's in the optimization problem, then none of the ZITs interact with each other at all, right? If A is fixed, that fixes this first constraint, and then I just have a sum over every individual ZIT in the optimization problem. So what that means is we can move the minimization over Z inside of both of these sums over T and I without changing the optimal solution at all. I can just think about it like in parallelism, right? I can, I can individually, like each of these ZITs is like a different thread, right? Like I can, and they don't care about the values of each other. So I can completely move this minimization. That was not exactly the animation I wanted, but I wanted to just show that I could move this minimization over Z into these sums, given a fixed A. So this is the exact same optimization problem because of the separability of Z. And let me move all the constraints that have to do with Z inside of this minimization problem. Now notice that this inner minimization is actually just a clipping, or 1D projection on the box constraints if you're fancy, but it's just clipping. So let me show you. It has this solution. So the optimal solution just clips QIT plus 1/2 to be between 0 and AT. This makes sense, right? We want to set Z to be as close to QIT plus 1/2 as possible, because this is what makes this expression inside of the square 0. but we can only make it as small as ZIT as small as 0 or as large as AT, which is why we need to do the clipping, right? So I'm trying to cancel out QIT minus 1/2 with QIT plus 1/2. Now we need, now we can plug in this optimal solution to this minimization problem and remove it. This will give us 3 cases. For the case where QIT plus 1/2 is less than 0, the lowest we can make Z is 0. So this leaves the following remainder inside of the objective, right? So if I set Z to 0, then we have QIT minus 1/2 squared, which is, sorry, that should be, oh, sorry, that plus should, that should be it. Yes, I think I got the sign slightly wrong there. Yeah, sorry about that. So yeah, if you just put a 0 here, you should be left with negative QIT minus 1/2 squared. Oh, but I guess you could just take the negative out, right? Because you're squaring it. So anyway, yeah, sorry, no bug, this is fine. Okay, then if QIT plus 1/2 is between 0 and AT, then we can set ZIT exactly to QIT plus 1/2, and the objective becomes 0. And then again, if QIT plus 1/2 is larger than A, then the most we can set ZIT is to A, and we get this. This is really interesting because it shows that the first 2 cases actually don't have AT in the objective at all. So these cases are constant with respect to the outer optimization over A. So we can ignore them without changing the optimal solution. Just forget about them, right? They don't have A in them. So this entire minimization over Z simplifies to this final case. Only when QIT plus 1/2 is greater than AT, we have this term in the objective. So let's put that back into our original optimization problem. So now I'm just summing over i's for which this inequality holds, and for any of those i's, we just have that term. So we've completely removed the optimization problem over Z with this new term. So now it's just an optimization over A. And remember, when we find that optimal A, we can find the optimal Z with projection, with clipping. Now the question is how to solve this optimization problem for A. Now notice that this constraint is very annoying. Without this constraint between the A's, this entire optimization problem would be separable again, and I could just solve for every individual AT independently. But as soon as I have this parental constraint, then it's not separable anymore. So it turns out that this optimization problem can still be solved efficiently. The first observation is that this is an isotonic optimization problem. You may have seen isotonic regression before. It looks something like this. It's regression, but instead of having a single line like the green dotted line to fit your data, it requires predictions to monotonically increase in the independent variable. So you get something like the red line instead of the green line. This always has to, as I increase the independent variable, I'm always like X, I always have to increase my prediction. Here we're not doing regression, of course, but the constraint is very similar. The A's have to monotonically increase as you go from the leaves of the tree to the root. It turns out this can be solved by a generalized isotonic optimization problem introduced by Yu and Jing called generalized pool adjacent violators. I'm going to explain quickly how this works because I think it's an extremely cool algorithm. Let's first just ignore this isotonic constraint. Now we get a separable optimization problem over A. So we can optimize each AT independently. So let's just look at one of the, first, do you believe this? None of the ATs interact with each other, right? And we just have sums over these ATs. So this is separable. So this is a 1D optimization problem. The first term of the objective wants A to be small, but making A small makes the second term large because more i's are going to be included in the sum, right? The QIT is more plus 1/2. More of these are going to be larger than A. Now what we'd like to do is take the gradient, set it to 0, solve for A, the classical thing. But the problem is the number of elements in this sum depends on A. To do this, what we're going to notice is that there's some optimal A star. For that A star, let K star be the optimal number of points for which that are in this sum. And only the points that are being included in the sum are just the largest QITs, right? All of the others are going to be smaller than A and will be forgotten. So what we can do is we can sort the Qs from largest to smallest. And we'll just, just for notation, we'll just define S as the largest K indices of these Qs. And now what we're going to do is we're going to remove this A from the sum, and we're just going to solve this optimization problem for different values of K. So let's say, K is 1. So I'm just taking the largest Q and I'm just summing over. I'm just, there's no sum. It's just the largest Q and I'm computing that value. And that's the value of this objective. And then I can do for K equals 2, I can take the 2 largest Qs. So I'm just defining this objective depending on K. And the reason I'm going to do this is because we can take this objective, we can take the gradient set to 0, solve for A, and we get this. And this is AK because it depends on how many Qs you've included. So given some K, the solution is essentially just to average the top KQ values. Now it's easy to show that as K increases, this objective function increases. So we really want, in order to minimize A, we want K to be as small as possible. The only condition is that when we solve for AK, we need to make sure that there are exactly K points that satisfy this condition. So specifically, let's say we set K to be 1, we know the optimal value for A1, we took the gradient and everything, it was this average, and let's imagine that value, A1, was here. Now, this value doesn't satisfy our assumption, which was that there are K values that are larger than A. They're actually instead of there being one value larger than one Q value larger than this A, there are 2. So we need to increase K until this this assumption holds. So let's imagine A2 was here. Now, this is the optimal A for when there are 2 Qs larger than it. And we find that there are, in fact, 2 Qs larger than this A. And because this is the smallest number of, this is the smallest value of K for which this holds, this has to be optimal. So that's how we're going to solve this separable problem. And the cool thing is all this requires is sorting, which is, n the batch size, t the number of tree leaves, so that log that. So sorting is extremely fast. This is very easy to solve. Now the second step is to deal with the isotonic constraint, and here's how that works. The algorithm is called pool adjacent violators, and the reason is let's assume that for this tree, these values are the values of A. Now, And these A's are grouped. So the root node and the right child are 0.7, the left child and its left child are 0.9, and so on. Now, these values aren't ideal because we assume that the parent A's should be larger or equal to the child A's. But clearly, we have a child A larger than the parent node, this bold arrow I'm showing you. So the way pool adjacent violators works is it finds the violator with the largest A. That's this node, T max, is 0.9. And then it's going to merge that group with its parent. So it's going to merge the 0.9 group with the 0.7 group, the child group with the parent group. And then once it merges those groups, it's going to solve the optimization in step 1. The one I showed you that does the averaging and increasing values of K. But remember that optimization is separable, right? So we just have to solve for a single A value, and we're going to assign that value to all of the nodes. Once we do so, yeah. So let me just make this clear again. We have this green group and this purple group. We're going to consider only those nodes. I'm calling those groups G and G prime, and it solves that optimization step in step 1, but only for those nodes. So we're going to solve this optimization problem as separable, and when we solve it, we're going to solve for a single value, and we're going to set that value, all those nodes to that value. And so here's what we might get for that merge. We might get that they're all something like 0.8, because right, I told you it's sort of like an averaging the optimal A. And we're going to do this basically until all of the A's satisfy the isotonic constraint. So at most, this is going to require T steps. So alternating solving the first step, then doing this pooling step, and then going back to that first step. So this is an alternating optimization problem that cleverly takes into account the isotonic constraint. When we compare this with a generic approach for solving A using something like CVX pi layers, that black box method, then our approach is much faster because it's just this sorting followed by this linear method, alternating, with at most T times with that pooling method. Whereas the black box CVX pi layers just says, well, this is a QP, I'm going to use standard QP methods to solve this problem. So this is, as n increases the size of our batch, the time stays very low, computation time. In fact, it becomes, yeah.
I have a question. So this case, can we get the exactly same solution of CVXP and yours?
Yes, exactly. So the quadratic program, that's right. The original problem will be exactly the same.
Okay. So basically, yes, the final solution you can get almost same, and your method is much faster.
Right. Exactly. This problem. That's right.
Thanks.
Yeah. Yeah. Thanks for clarifying that. So I should have made that clear. So quickly, the way we're going to solve this problem, this is the entire optimization problem that we are trying to solve. We have an efficient way to solve for the discrete parameters using isotonic optimization, like I just showed you in those steps. And this objective is fully differentiable with respect to theta. The gradient with respect to theta propagates through the minimizing path by Danskin's theorem. Let me call this program T lambda as a function of theta. And so to learn the continuous parameters, all we need is some loss function, L for the task, squared loss, something like that. The predictions of this loss are given by a predictor, which is just going to take as input the optimal Z's that were solved for, and potentially also the data as well. It doesn't have to have Xi, but you could have it. And the overall learning algorithm is simple. You're just going to grab a batch of points. You're going to compute the discrete parameters Z and A using the isotonic optimization method I described. Then you're going to update the continuous parameters by taking the gradient of the loss with respect to theta, which is in Q, and phi, which is the predictor. And you're going to keep going until some stopping criteria. So took a slightly longer, sorry, let me go through the results really quick. And let me frame them in the motivation of the talk. So let's look first at the efficiency and the generalization. So this was for classification. These are to benchmark tree classification data sets. CART gets about this, so we're hoping to meet that. These are mixed integer programming methods, excuse me, and they, in the time that we trained them, we used 64 gigabytes of RAM and trained all methods for 3 days. They either overflowed in memory or in time. These probabilistic methods we compared with, they got these sorts of accuracies. So I would say NDF and ANT, you know, they're doing the best on Higgs so far, and NDF is on click. And this is what we got for our method. And I should emphasize that for all methods, we use 20% of the training set for tuning hyperparameters. We do it 80-20 split of the training set. And for all methods, our methods, excuse me, and probabilistic methods, we use a state gradient-based optimizer. And this got us pretty excited because we were able to improve a lot of the changes we made were to improve memory efficiency and hyperparameter tuning. We only have a smaller number of hyperparameters, I would argue, than cards. So we would have been happy to match state of the art, but we're able to improve upon it. So how does this compare to ensemble approaches? So it's not as good. So ensemble, right, will have the best performance in the dataset, but it's quite close, I would argue. And we're just using a single tree. Our split functions aren't linear. We are learning, well, no, so they can't. I think we did hyperparameter tuning with linear or like LU splits functions. And then we have this nonlinear function on the predictor function on the outside. When we look at training time, CART is super fast. We're not going to be CART, but when we compare it to these other approaches that finished, we get something that we're hoping for, something that's not as fast as CART, but faster than these other methods that are based on mixed integer programming or probabilistic training. We get something similar for regression. We're a bit farther away from the ensemble methods, I would say, but I think we could approach that maybe with a bit more tuning. And we get something that's not as fast as CART, but faster than probabilistic work. We also said, why not try this for hierarchical clustering? Because we could use this for any loss function. So we compared this to classical and recent methods in hierarchical clustering. And in the GLASS, this is an objective we want to maximize, sorry. This is dendrogram purity. So ours wasn't the best on GLASS, it was second best, and we were able to achieve state of the art on cover type compared to these methods, which I thought was quite encouraging because we didn't really have this in mind when we were initially designing them. So I'd argue that we were able to achieve these first and fourth objectives. Let's look at the third. Let's see what these trees look like. So lambda is 1, we don't have a lot of pruning, this is what they look like. This is what the coloring is meant. So darker red means A is closer to 1, lighter A, or off is A is 0 and lighter is approaching that. This is sort of the main path, the most popular path. And as we increase lambda, we see that path being retained and some other nodes being pruned. So we can also look at the distribution of classes. So this is the glass data set, and these are two very similar glasses. They're being routed on the ends of the tree mostly, whereas these sort of different glasses are being routed down different paths. So let's look at memory. This is when we increase the dimensionality, the memory stays rather constant, and similarly for n. So I think this is what we wanted. So now that I've bragged a lot, let me very briefly, at the end talk about some limitations. One thing is that sometimes when we optimize it, we get nodes where no points actually go, but they are not turned off. And this is suboptimal. Those nodes should definitely be turned off, and this is something that should be investigated further. A second thing is that we sacrifice finding optimal trees through this relaxation. And this plots how different the tree is from the optimal tree in different norms. So it might be nice to give it an approximation guarantee compared to the optimal because we added this quadratic regularization. So what I want you to take away from this talk is trees are very useful for real-world applications. Current tree methods make approximations that harm some aspect of their optimization or prediction. Our proposal is to divide these parameters of trees into two different categories and optimize them with different methods. This allowed us to drive efficient optimization problems that allow us to optimize continuous and discrete parameters. You can optimize these trees with any loss function, and this helps in accuracy and speed compared to other methods while staying low memory and visualizable. So I'd like to thank my co-authors, Valentina and Vlad, and thank you all for listening. I'm sorry I ran over. I'll take any questions you have now.
Thanks, Matt. It's very, very interesting. Lots of ideas.
Thank you.
From the audience, do you have any questions at this point? So if you have any question, please feel free to just ask Matt, or you can just type questions to the chat. For now, I have one quick question.
Yeah, please.
For the experiments you compare with your single tree to the XGBoost. So is it possible to just, maybe it's easy to just create a random forest, for example. So in that case, is it possible to improve the performance, or just the performance is kind of similar, or do you have any experiments? Or
you're talking about ensembling this method.
Yeah, right.
Yeah, we didn't do that. It's a very good question. This question has come up. I wish we would have done it because this question has come up so many times. So it's definitely something we should have tried, but we haven't done it yet. I think this would be really cool to do because you could do something like you were suggesting, like random forest or boosting, where you actually train on the sort of the errors of the previous tree and fix that. Or you could even train both. If you have enough memory and computation, you could train multiple trees at the same time. All that would change is sort of the prediction function. But yeah, we didn't end up doing that. I think that would be really interesting to try.
Okay, thanks. I just wonder. And so I have one other question. So you compare the time, and so which part is the most expensive? So there's a time comparison, right? So then.
Go back. Oops, sorry. I have 1 second. Yes, you're talking about. Let's go all the way back. So there's one for regression and one for classification.
Yeah. So I saw that your method is super fast, but so this seems still like a big gap from the cut. So which part
Yes.
is the most expensive?
Oh, right. So what's the bottleneck? Yeah. So I believe the bottleneck is, I think it's probably the integer linear program. So the tricky thing here is, so you still need to do this sort of sorting, and you might have to do it the number of times that you have tree methods. And so it's hard because it's not easy to parallelize. You have to do this alternate. You have to sort your Q values. You have to then merge. You have to pool adjacent violators. Then you have to consider different Q values. You have to sort those. So I think, basically, if right now, because this is not really made any faster with like a GPU, this sorting and alternating. I think this is probably the bottleneck.
Okay. I understand. Okay. Yeah, thanks for the clarification. Okay, I think I have. So from the audience, do you have any questions?
Could I ask a question?
Quite fast. Yeah.
Hi, thank you for the nice talk. I have two questions, and one is kind of an obvious one, but in terms of the error, you showed that your method improved upon the baselines, especially in the classification task, and also the regression. And is there some intuition why that's occurring here?
Yeah, I think so. My intuition, so let me make it a bit sort of clear the way some of these other methods work. So Ant is this method that greedily grows the structure of the tree, but then it will, after it changes the structure, it will re-optimize the parameters globally. So so I think potentially one reason is that this tree structure growing is suboptimal because of this greedy growing, whereas we're trying to sort of optimize all of the discrete parameters and the continuous parameters. I think this method is also a bit flexible. So whatever predictor you want at the end of your model, you can have. And what we ended up doing is, as input, we took the data, we took the Z's, and then we used like a neural net, and we actually did like a residual connection so that like you create some representation. And then I think trying to remember how this. No. Sorry, we didn't do that. You just create whatever sort of predictor you want on the end. I think that probably helps our method. Whereas like a lot of tree methods, they usually don't take in the data as well, and that might have also helped.
I see. That makes sense. Thank you. And the other question is, I'm sorry if this is like a newbie stupid question, but let me first confirm that your method allows you to compute the gradients with respect to the parameters even after the training, right?
Right. Right.
So I was wondering, my question is there a possibility that you could compute something like the importance of each of these parameters, like one specific node or some one specific, like how do you say, branch after the training, like finding out which parts of the learned tree is important in producing the predictions?
I see.
Using that kind of, gradient information post training. That
Yeah, I
does that
think what
make sense?
right. So you're saying you have the tree trained, and what you want to do is you're going to take the for some point you're going to take the gradient of the loss with respect to
Some test
each of
input, right?
these
Oh,
split
yeah.
functions.
Sorry, yeah. With respect to, yes, exactly.
Yeah. And then look at sort of something like the norm or the
Right. Yes.
yeah, you could definitely do that. I haven't really given a lot of thought to this, but certainly after the tree is trained, you could absolutely take. So yeah, basically what this lets you do is take gradients with respect to split functions and phi. You could do it with respect to
Yeah.
q as well. Yeah, so any method, I guess, that relies on continuous gradients for SV importance, you should be able to. You can take gradients with respect to Z and A, but you could use the other ones. Yeah, I haven't given this much thought. Sorry that I'm not very familiar with these methods. With sort of importance judging methods. Sorry.
Okay, well, I'm not an expert in that either. I'm just wondering. Thank you.
Thanks for the question. Do you have any further questions?
I guess I should also maybe add to that question. I think another way you can see importance, I guess, is the final. So you get these final discrete parameters, right? So these will be ideally sparse. You may not have a specific path, but you may for a specific point, you may have like one in a partial path, or potentially even, and this will change your final z. So you may get this vector that is not exactly binary, but and that will tell you at least sort of which parts of the tree that point is being sent. So that, and then if you want to know more about like the tree structure itself, these A's are going to sort of give you how important. So yeah, I kind of went through this really fast, but these A's are going to tell you sort of which parts of the trees are being used, hopefully more than others. There are these weird bugs where A's will be not 0, but no points go there. So there's definitely something that I think maybe needs to be sort of thought a bit more about for those nodes. But yeah, I think that's how I would that's one way at least to judge importance.
I see. So yeah, I see. Even without taking the gradients, you can already interpret these. That makes sense.
Right. Yeah. Yeah.
Thank you.
Any other questions? Okay, seems like we have many questions. So thanks for the, okay. So then, yeah, it's really nice talk. I really like it. And yeah, also I just one comment. I really like the idea to just learn at other planets. It's maybe like a new potential new machine learning programs.
I'm so glad.
I have never had this one before. So okay. So
awesome. Yes.
Okay. Yeah. So then let's start the math again.
Thank you, everyone.
Thank you very much.
Thank you for the comment as well.
Yes, I love that figure.
Thank you. I spent some time on these things, so it's nice for you guys to notice these things.
So maybe if you have time, maybe we can chat here. Also, this is the end of seminar. So maybe if you want to chat with Matt at here, maybe you can stay. And otherwise, this is the end of seminar. Also, so this is If you're interested to join the Weekend AIP channel, please register it. Thank you.